Nature is amazing, and birds are amazing creatures, but we do not fully understand yet how they can fly. Could we really understand the magic of flapping flight so that we can build robots that can fly better than the robots that are currently available? The rowbird is the only robotic bird in the world which can fly in up to 5 Beaufort wind and at a speed of 80 kilometers an hour. It weighs the same as a peregrine falcon, and it looks like it, but do we really understand the underlying physics? We believe that flapping flight is achieved with a combination of flapping and twisting of the wings, which creates detached vortices which generate thrust. But are we at the moment using the optimal combination of the oscillatory pitching and plunging motions of the wing? To answer this question, an experimental setup is built in the wind tunnel of the University of Twente to see how the wing moves and how the stream of air moves around the wing while it's flapping. This allows for exploring the optimal wing motion for the rowbird. A helium-filled soap bubble generator is installed which blows thousands of bubbles per second into the wind tunnel. 4 high-speed cameras film the bubbles to capture the movement of air around the wing with the shedding of vortices. Furthermore, a force sensor at the root of the wing can measure the resulting forces on the wing, like lift and thrust, and reflective markers on the wing can be filmed with cameras to track the wing movement and deformation at a sub-millimeter scale. We have studied the flexibility of the wing since it's an important part of why the rowbird flies the way it does. Different than many people think, intelligence can also be embodied in the material and properties. A brain without a proper body is useless for locomotion. We want to bring this physical intelligence in the wings of a robotic bird, and in order to do so, we created smart wing designs and smart mechanisms which are able to change the mechanical stiffness of the wings to change the flying behavior. But how can we precisely describe the physics of a robotic bird with deformable wings interacting with the air around it? The unique feature of the approach we followed to describe dynamical physical systems is that it relies on energy and geometry. Energy is probably the most fundamental concept unifying the various branches of physics and explaining how nature works. In the Portwings project, we used the Port-Hamiltonian framework to get insight into the energetic fundamentals and transport phenomena of fluid dynamics, structural dynamics, and fluid structure interactions. In the Port-Hamiltonian framework, we describe any complex physical system as a network of energetic modules interconnected using power ports that characterize the energy flow within the system or exchanged with the environment. For example, if we consider the flapping wing setup we developed, we describe it as a network that represents the dynamics of the driving mechanism, the elastodynamics of the wing, and the aerodynamics of the air around it. The power supplied from the power source flows to the electric motor, and then some of it is stored as kinetic energy in the mechanism's inertia. Some of it is dissipated as heat and noise, and the rest goes to the flexible wing. The power supplied from the wind tunnel is also transferred to the wing through the moving boundary of the wing and the airflow injected inside the wind tunnel. In each cycle of the wing's flapping, the power supplied to the wing oscillates between kinetic energy and elastic potential energy, while the power that flows to the air is either stored as kinetic energy or dissipated in the vortices formed due to the wing's flapping motion. Our Port-Hamiltonian description of this physical system differs significantly from the standard approach of continuum mechanics using coordinate-based tensor calculus treatments. We rely instead on coordinate-free exterior calculus and describe the network structure of the system using so-called Stokes-Dirac structures. This methodology allows us to intrinsically handle open boundary conditions and thus use, reuse, and combine sub-models in such a way that a real Lego of physics would be possible. Consequently, this leads to the development of structure-preserving computational algorithms that allow us to efficiently and robustly simulate these physical systems to produce predictive computer models of the world around us. The real advancements in science and technology are only achieved with a deep understanding of the fundamental theory, as well as proper engineering and experimental skills targeted to the goal to be achieved.
I'm very happy and thankful to the European Research Council that has given me the opportunity to build an exceptional team with which together we have been reaching results which would be very important for science and engineering in general, and not only for understanding the nature of flapping flies.